So this is the third section of our SolidWorks What's New in 2015 series. And we're going to start off with just a little bit of discussion based on some PowerPoints. But we're really talking about reducing operational costs, whether that happens to be analyzing the types of costs that you have associated with the creation of your products, or the actual consumption of raw materials. So there's a few different things with respect to that. And it all boils down to cost. Time is money as well. We're going to start with some 3D printer capabilities. Now, 3D printers are not new. In fact, they've been out since mid-'80s or so, but they're really gaining a lot of traction. In fact, today you could go to Office Max or Best Buy and actually buy a 3D printer, an FDM-type tabletop model. Windows 8 actually has some 3D printer drivers built directly into it, so this is going to get pretty mainstream for a lot of users here over the next 5 to 10 years. Now, I don't have Windows 8 on my machine, so I'm just going to simply show you the screenshot. But it shows up as a Print 3D option in SolidWorks. Instead of saying File Print, getting your HP DeskJet, you're going to get File Print 3D. And you'll be able to choose some settings for things like the MakerBot and the Fabricam, which is FDM-type models. Settings for quality, layer thickness, and other types of operations. Now, we've always had the capabilities to say File Save As, STL, and then bring that stereolithography file into a preprocessor post to SolidWorks, but pre-3D printer. Makerware has their application. There's also some other applications that are used to pre-process and format the way that the quality of the print is going to be. But this is built directly into Windows. Next thing I want to do is talk a little bit about costing. Any of you that have professional or premium SolidWorks seats have SolidWorks costing. Now, costing up until this point has been part really just relegated to things like a sheet metal part, fold, unfold. There's dollars associated with the lengths of the cuts, so inside and outside water jet or plasma type cuts, and then what a fold or a bend is going to cost. So you can set up templates in order to analyze things relative to that. But also machine parts, and those could be milled or turned parts. But they have to do with the comparison of how long it takes, so speed and feed rates come into play, and then the amount of material consumed and the amount of scrap as a result of that. And those are generally what the costing applications do. And we set up a couple of templates in order to have some of your internal costs really specific to your needs and capabilities. Well, this time around, costing has really opened up a lot into what it can actually do. What we can now do is costing of weldment. These weldments are going to associate things like the length of a piece of structural steel with the types of stock that you might keep on the shelf. Might be comparing a particular length of a square tube to an 8-foot stock length that you might have. Therefore, if it's over half, then you can't use two of those or one of those to make two pieces, so you'd end up with a scrap value with those. But there's a lot of things that go into making these templates, and we ship some default ones that all you have to do is tweak and customize them to your particular costing needs. So we do that with the weldments, but we now also do the costing of a cast component. A cast component's going to have much less scrap because it's not taking a block of steel and then milling it down in order to create a part that looks like this. It's going to be, more about the residuals that we have over here, maybe some of the extra materials that we need in order to fill a cast. But there's some other material utilizations and time and material costing values associated with that. Now, we also do the machine parts as well, but we can now compare those machine parts to a stock body, something other than, say, plate steel, bar steel, or a block steel. You can actually use the cast component as your stock body, and obviously that's going to have a big effect on how much scrap you have, since we're only going to be cleaning up a few holes and maybe some datum faces, but not necessarily machining this from a solid block of material. So great little enhancement there. We're also doing costing of 3D printed designs as well as plastic injection molded designs, and both of those have different types of scrap. 3D printers have consumables, generally in the form of a support material. Each material has a different way that it's either removed or broken away from the parts, but that's going to be a scrap cost. And then you also have plastic injection molding, where their scraps would come from things like the runners and screws. But injection time, part material utilization, all of those kind of things are going to play into the costing setups of those. So that'll get more and more traction as people start to utilize it. But the key to this is if you spend even a few hours a week trying to estimate the costs on parts that are similar to ones you've done before, I'd recommend you take that time and maybe either explore or set up the templates to associate with what you do, and then maybe at time will then lead to something where it's just a button pick away from a cost estimate instead of those couple of hours repetitively week after week. So if it is a significant part of your business, you can get a handle on that with the software you already own. SolidWorks Model-Based Definition has just become available. In fact, my slide up until this morning said available Q1 of 2015, which we are now in. SolidWorks Service Pack 1.1 now has this available to anybody that's purchased it. Now, this is something that can be bolted onto any seat of SolidWorks. And what it's used is for creating what we call model-based definition files. These are really more or less PDF files, but they're PDF files or e-drawings, frankly, that contain a lot of communicative data for other people downstream. Now, it could be somebody that's in inspection, it could be in manufacturing, but it's somebody out there that's going to need the SolidWorks or 3D data, but maybe doesn't have access to a SolidWorks seat. So what MBD is going to create, based on templates that we supply, and there's dozens of these templates that are fantastic and laid out with different formats of thumbnails and views and where the view interactions happen to be. But it allows you to go ahead and use a template to go ahead and extract the SolidWorks DIM Expert dimensions. So with your DIM Expert tool, which has been in SolidWorks for half a decade now, you can go ahead and scheme a model for manufacturing. And these are dimensions that you would add that would be relative to datum faces. They'd have GD&T. They would also have full tolerancing on those. These DIM Expert dimensions have been used up to this point for annotation views for drawings or for the Tile Analyst tool, which is also part of SolidWorks Premium, has been for a long time. Well, these dimensions here scheme the part differently than your sketch and feature dimensions, because generally a sketch and feature dimension in a parametric system is set up so that you have predictable change when a dimension is modified versus the dimension that you'd use for manufacturing. Many times, most times, they are exactly the opposite of that. But essentially, when you scheme your parts out, you can then inject your part into one of these templates, and you'll have a PDF that you can send to anybody with a computer, Android device, or iDevice. And they can open up this file, they can rotate it around into its flat positions, and even go ahead and maybe have an attachment of the 3D CAD geometry built directly into this as well, like a step file. But in any event, it's for communication. It's going to have some fantastic capabilities that even SolidWorks alone doesn't have, like broken views for very large framing assemblies, in order to make a very large component maybe sit in a smaller viewable area. It's a lot easier to interpret in that way. So the tool itself is available. If you do want to see a deeper demo into this, please contact your sales representative and we can connect you with a WebEx meeting or a GoToMeeting and show you what this product is all about. Military has been using that for quite some time, by the way. It's more or less a black box where all of the enterprise data is available within those PDF files. All right, let's get back into some more modeling specific things, some SolidWorks basic stuff. We're going to show you some things about how to enhance building infrastructure support for those of you who build devices that are maybe fairly compartmentalized or palletized size for you, but maybe go into a larger facility. We'll talk about that in a second. Dealing with different types of improvements to complex capabilities in SolidWorks like surfacing and sheet metal, and then some fantastic new pattern functionality. Let's just roll right into these. First I want to talk about is a technology called BIM. Now what that acronym really associates with is this discipline called AEC. It's Architecture, Engineering, and Construction. The device that you're seeing on the screen is, we'll call it a boiler or a heat exchanger, but it's fairly compartmentalized in size. However, this heat exchanger is going to go into a large facility, factory, stadium, something extremely large. And that's what these BIM products or these AEC software products like Autodesk Revit are actually designed for, is ridiculously large-sized facilities. So what happens with all of this is we build the models in your CAD tool with all the detail that you need. Now this detail is fantastic to build because you're going to need to know where the fasteners and the lifting lugs and all of the other components happen to be. But when you're looking at a stadium with 20,000 seats or a large factory that covers several football fields, this kind of detail will be devastating to your performance. So we want to set these files up so that they have a lot higher performance, but they still fit the bill for what they need to represent. Because when you're looking at it like this, the detail is necessary. But when you're looking at it like this, the video card is taking the hit, but you don't need those hex head bolts. In fact, there's hundreds in this part that are going to just kill your video performance. So under your Tools pull-down menu, next to D feature, which is a lot of what AEC actually does, but it's called Export to AEC, Architecture, Engineering, and Construction. It runs you through a process here. Now, the first part here is orientation, and the reason this exists is because we are based on Parasolid modeling kernel. And when you export to an AEC product, Autodesk Revit we'll use as the example, they are generally based on the SAT, the ACES kernel. And ASYS defaults to the top plane, like you're looking at the Earth, which is a lot of what 2D architectural civil engineering products do. However, our Parasolid modeling kernel-based products like SolidWorks and Solid Edge and Unigraphics, they all default to the front plane. So when we export this file as is, as a SAT file or ASYS file, it actually goes into the other products on its side. So the first thing we're going to do is orient this based on floor, ceiling, or wall, whatever this is going to sit on. And we'll just do that by simply picking the bottom of this foot, and that's going to be the floor. And then we'll just give it a datum, lower left-hand corner, origin of 0. 0, 0, 0. The next step it runs you through is the model quality. And you can choose some defaults of high, medium, or low. But if you trigger custom, what's going to happen here is it runs you through the defeature tool. Now, the defeature tool allows you to automatically remove internal components, and if you can't see them or see them mostly, even though this has a hole in it, some of these parts are deemed internal because the camera points around this assembly. Many of them cannot see these parts, which would make them an internal qualified part. But you can also just say simply small parts, a particular percentage of the overall size of this assembly, or even combinations where physically selected parts like this handle don't need to be there. When we go ahead and take this and update by removing the things I've selected, so parts that are less than 6% of the overall size, and then part specifically selected, it will scrub those off the screen for us. So what defeature also is useful for is actually removing internal details that are maybe difficult to remove with things like suppressing features or extruding over top of features to conceal internal details. Defeature is something you'll want to try if you do want to send files out, but scrub some proprietary information from those. So here it's removed a lot of things. Got rid of the handle I selected. You can see that all the heads of those fasteners are gone. And when we select next now what we're going to get is a choice of features to keep. Now this would be things that are critical. In this case, I'm actually going to select the holes in the mounting feet because those holes are going to be bolted to the floor, and regardless of what this is, I want that hole pattern to be useful downstream. Now when we say go, it will take the criteria and remove everything else insignificant. So it's going to take features out of parts, it's going to take parts out of the assembly, and the result of which is going to be what you see on the right-hand side here. So first thing is it's on its side, which in an AEC product is actually the right orientation for it. It would actually roll around and be on its end. The second thing is you can see a lot of the internal detail that's been removed. As I roll this around, there's a lot of parts that are gone. Most of the stuff that's up on the inside is gone. Not everything's there. But the fastener holes over here on the side are completely removed as well, even the holes inside these lifting lugs. So you can see exactly what the results of this tool are. Now if I click Next, my choice is to save this as an ASYS model, which again is the file choice of type for Autodesk Revit and other AEC products. And I won't continue with that. But the idea here is to prep your files for consuming downstream in these larger scale but less detail-specific applications. Next, I want to talk a little bit shortly here about changes to routing. Now, routing has been in SolidWorks Premium for quite some time, and it's always been based on tubing, piping, flexible tube, could be conduit or bent tubing, but then also things like flanged tubing, PVC types, copper that's sweated, or threaded pipes. So there's a lot of varieties of ways that these things connect. Well, two new libraries have been added to SolidWorks 2015. One is for rectangular ductwork. It's going to contain things like elbows and T's and crosses, as well as reducers for different sized ductwork. Works exactly the same way that routing did up to this point with piping, only it's a different type of component. Same is true with this new one called cable tray routing. Works exactly the same way that routing worked previously by giving you automatic lengths of items, quantities when it comes to a bill of materials, and even custom things if there is an odd angle that you might have to deal with. But essentially, it is a simple component library that bolts right into the existing routing functionality that's already there. Cable trays are usually those trays that are hidden above and around walls and drop ceilings that have infrastructure like wires and cables and network wires and things like that. Next one is Weldments. Now, Weldments has been around for a long time, and it never ceases to amaze me the amount of things that we can add to it and enhance it to cover more elaborate use case scenarios. And today is no different. So I want to show you some new visualization capabilities, some fantastic gusset enhancements, places it never would have worked before, and then some end cap creations. And then we'll move over to things like weld beads and the way the cut list now functions. So for any of you that use Weldments, cut list functionality is probably one of those things that you can deal with and work with, but it's not the most user-friendly more or less can be a little bit distracting or difficult because of the generic naming system. We're going to cover a lot on these particular topics. So let's go right back into SolidWorks. We're going to go ahead and open up this Weldment. Now, the Weldment that I'm looking at currently is a single part file, as all Weldments are, and this single part file is based on just our basic structural library, but it's got a mix of different things. We've got some sheet metal components over here. We've got round tube and rectangular tube and plates, the basic things that you would see in a lot of welded structures. First thing I want to talk about is a little bit of the interface when it comes to the actual creation of the structural members and the groups. First of all, you can see what the groups are of the components on the screen a couple of different new ways. If you select the group, they highlight not only just the path down the middle of the components, but the actual bodies themselves highlight in yellow. You can also hover over the components on screen and you'll see what groups those components are part of. So really simple, I don't even have to scroll through it to see what groups each of these bodies happens to be a member of. So visually, that's a great improvement. Second thing I wanted to show you here actually had to do, and let's go back into that again, was a change that was made to our corner treatments. If we go ahead and take a look at this corner treatment bubble, and anywhere there's a magenta dot, not only Weldments, but also in patterns or sheet metal, those are points at which you can individually action on those particular locations, which means global settings aside, you can be very refined and detailed specific to the point we're selecting. So when I select this particular corner treatment, what I want to do with this is just go ahead and show you that first of all, the trim order is listed next to the groups themselves. You don't have to scroll through and watch this box move from 1 to 2 to 3. So simple thing, but a lot of the simplistic changes to the software really have a lot of teeth because they cover annoying things or access to information, which this one does. This box also is now what we call non-modal. Before, when this box was up, my graphics would preview, but that was locked out of things like zooming and rotating. Well, now I can actually do that while I am midstream into this box. So if we want to see this a little closer, maybe we want to go ahead and change the trim order of something, for example. We change it and we see the preview right away. We go ahead and start changing this one here and changing the trim order. We'll see some pretty drastic changes to that preview as well. But I can see that either in the orientation I opened this box in or in any other orientations that I choose. So that one there is quite helpful. But being non-modal is obviously the most important part to being able to interact with that without really knowing what you want to see before you actually see it. All right, let's go ahead and move over to a little bit of our gusset capabilities here. Gussets are something that obviously work in perfect scenarios, but everybody does things in a unique way, and they don't always stack up into a nice little bucket of usable use cases. When a gusset functions every time, this is the type of situation you'd see it in. So let me start with that. Grab your gusset tool off your Weldments toolbar and select a couple of adjacent faces. Preview shows up where you can then go ahead and determine the thickness based on left, right, or mid-plane. Also, orientation can be left, right, or mid-plane of those faces. So nothing really new to those. Let's make this significantly larger, though. Okay, that looks pretty good. Say OK to that, and of course it's going to create that piece of plate gusset right there between those two faces. Other cases, though, are ones where we've really had some difficulty with in the past, and they have to do a lot more with non-planar faces. Obviously geometry that's not either coming to a virtual intersection or having a nice concise intersection point defined. Well, these cases are now available in SolidWorks 2015. So we'll use our gusset first of all to go ahead and select a couple of round parts. So now on this tube steel, it's going to build a gusset that's going to be tangent to that round face. These arrows that show up allow you to actually switch the sides, which of course doesn't make any sense in this case, but it does allow you for some orientation control. We'll do gusset again, this time between a flat face and a round face. Now, there's no preview initially on this. The reason being is because it doesn't really know the orientation between these. It could be above, it could be below, and frankly, this face could be infinite in all directions, so it could be almost anywhere. So down here you have a location capability that gives you the option to choose an edge, and that edge will act as a vector. So if I grab any edge going in the proper direction of my rectangular pipe, we'll see that that gusset is inserted properly, just as if it did between these two circular tubes. That one also can be flipped to the bottom side. There was the same type of arrow on that. Probably should have showed you that. This one does make sense. So flip it to one side, flip it to the other. So all those things work really nice. Now, believe it or not, this is probably one of the most common use cases. You've got a plate that you've added to a welded frame, and this is one of the ones that really had trouble with. And the reason is because it's not a square plate and a rectangular tube coming together. It's a square plate and a rectangular tube with radiused edges. Therefore, the virtual intersection between these two actually goes into that corner. It's a really interesting situation. Well, this is now very, very expectable in the way it works. Sorry, I made up a word there, but this is a simple thing. You go ahead and select a couple of faces, and just like the two rectangular tubes prior, it builds the proper adjacent gusset between those two faces. It's now extending this face to the virtual intersection in the plate. Now, those types of use cases for gussets were also challenges for our weld tool. The weld tool has started changing in a very, very positive way back around SolidWorks 2010, where we switched from the fillet weld to the weld bead function. And the weld bead is more of a virtual weld. Virtual meaning it doesn't physically create solid geometry, but you do get feedback for the length of weld, potentially the weight and cost of that weld, and then the auto weld symbols for those as well. But it works in much more odd places because it doesn't create solid geometry, therefore it doesn't need the perfect setup to create a sweep or adjacent geometry lofting or things like that. So here we're going to use the weld bead in some of these new cases. The basic way we would use the weld bead would really be to select components and group them together. So as I select my gusset and I select my two pieces of circular tube, we're going to see the virtual intersection that's generated between those. Once we define the proper radius of this, we don't have to exit this tool if we want to continue to make additional weld beads with the same settings. What we do here is we go ahead and say new weld path, just like we would say a new group creating our structural steel. So new weld path will allow me to go ahead and select other situations. So over here's another one that was a little bit more of a challenge, user interface-wise before, was the selection between this part here and this part here. Now these have kind of a stitch in the way that they intermittently touch, but it actually creates three individual weld paths where the three individual weld paths show up between these two selections. So single selection, but a lot more output with a minimal amount of input. Let's go ahead and do another new weld path. Up here we have two situations which were quite a challenge before as well. We've always, even with the fillet weld bead, had some capabilities to weld one part to another, but we've never had good capabilities of welding a part to itself. Here with a sheet metal part, we would fold that up, we'd weld those corners, probably hit it with an angle grinder or a belt sander and shave those right down, and they'd never exist. But we still have to represent the weld bead here in our CAD model. So the way we do this with our weld geometry, our original settings here, is we'd select a face on this side, and then I'd go ahead and select, say over on this part, we'd select an edge. And what that edge is going to do is give us the virtual intersection between those areas. So where this face and this edge come together in 3D space. Let's do one more new weld path, and this happens to be another one of those use cases. We have a rolled piece of sheet metal, which is again going to be welded back to itself. Well, here we actually can't use the weld geometry because we're only going to do a single selection. So we have a new radio button option that was added to the software called Weld Path. By simply selecting any edge of this vertical face, we're going to get a weld the complete length, and you can even do intermittent or stitched welds based on that edge selection. When we go back over another new weld path here to this situation, our common plate and our common structural steel, this gusset is very easy, but the weld on this gets to be extremely complex because it's not just a straight face, there's this fall off or this radius goes away from this face. So here's again where we use the weld path option. All I do is select edges, and those edges are all we need to put this in. In fact, I could sketch something with a spline or a circle and use that as a weld path as well. So if you want the welder to weld your name to a part, grab the spline tool and try and write your name in cursive. Basically, that's all it takes is any physical edge of solid geometry or even sketch geometry to make these. Once we accept them, we get this nifty looking weld bead out there. It's going to show up in all of those corners. We see that over here as well. And then as well as that, we got our sheet metal parts that are welded to each other at the corners. So great enhancements to the usability of that tool. I want to show you a little bit now about some end caps just real quickly here, and then I want to talk about the cutlass folder. It's probably my favorite part of this. End caps are nothing new to gussets, but recessed end caps are what is new now, and you can see one over here to the left. End caps have always been very simple. Select the tool, grab the face, and it automatically creates an end cap about the size of that face. There is a little bit of an offset ratio that we have when it comes to the size. But other than that, we can do things like adding corner treatments, where if I want to chamfer those corners or fillet those corners, we can ramp that up a little bit. But I can change this from an end cap, which is actually outward, to an end cap that is inward. We've had those before, flush to the outside face. But this is now a recessed one we call internal. Internal allows you to push that value back into the part as well. You can see it moving into the part. And I'm just going to put that in there 10 millimeters with a really, really minor offset here, because I want you to see what this looks like. When we say OK to this, what I found most interesting here is that we don't create an end cap that's actually going to take 3-axis CNC to create. Somebody was thinking about this. We make an end cap, and even though it's perpendicular to the end face and not perpendicular to the actual body because of the angled cut, we create an end cap which is actually perpendicular geometry so that it can be simply lasered out or single end milled out and then placed in and held and welded. We're not making a bevel on this face to make the end cap one of the more complex parts of this assembly. So good forward thinking by the developers in that case. So let's look over here to the left-hand side to our cut list. There's 2 things that we do for performance over here. One is I can right-click on this weld folder and actually suspend automatic rebuilds. Therefore, performance-wise, if I was to change the size of this assembly, those weld beads wouldn't necessarily update real time because that's a performance hit. You probably saw that it took a few seconds to generate those. You can click rebuild and then that will bring that up. But on the weld cut list itself, these are some things that I find significant. First of all, I've added some gussets and an end cap, and you see that these are at the bottom of my tree. Well, for anybody that's used this tool, I think that everybody assumes that there's an automatic update tool. In fact, I was of the exact same assumption. When you right-clicked the cut list tool in 2014, you would actually see a choice that said automatic. Now that automatic, unfortunately, was automatic grouping, though they didn't give us really proper terminology from the user interface from the developers. So I really thought that that was an automatic update as well. Well, now you see very clearly that there is a tool called automatic update or update automatically. By clicking this, I'll never have to readdress this cut list again. Those 4 gussets at the bottom and the 1 end cap will jump into folders that match other geometry sizes. But if I add additional things, those will also automatically jump into these folders. So that's the first most important thing there. There are a lot of Weldment settings that are actually under Tools and Options. So this is file specific. We'll go to Document Properties and then under the Weldments tab. Now what I've just done is I've actually turned this check mark on by the right click I did in the cut list folder. So automatically update the cut list. But one of the most important ones now in this release is this one that says rename the cut list folders with the description property. Because to me, cut list item 32, 38, 40, this means nothing. You have to interrogate it to figure out what it is. But if you click on rename and say OK, watch this. Those are much more appropriate, I believe. It's going to give you the size of the material, so it's giving us in this case the description of the profile that we used for the square or rectangular tubes, the plates that are in there for the foot pads, the plates for this plate, other plates here, even the gusset information. Well, gusset information is kind of interesting. It doesn't have descriptions of each of these. And in previous releases, this is something that's not new, but I'm going to go into properties and just show you this. If we look at any of the other plates, the plates automatically have these bounding boxes around them that give them length, width, and height and thickness. But these new ones that I've added, they only have material and quantity. So in SolidWorks 2013, what we added was an operation where you could right-click the cut list and say, Create Bounding Box. So watch cut list item 55 and 56 when I say Create Bounding Box. They rename with the description property, because what's happened is as we go into the properties, the bounding box has automatically detected the thickness, width, length, and volume and given us an associative property as well as a description using each one of those little property names. So we have this fantastic associative thing where if I change the thickness or I change the angle, 125 is the one length of my gussets, then you're going to see that that's going to update dynamically for you. So some really great user interface features which use better naming and automatic updating of things in the Weldment cut list. You also can right-click and save this assembly. So if you do want to save this out as an assembly, you can click Save Bodies. And this new functionality actually allows us to go ahead and take multiple parts of the same size and create a single part file, quantity of 4 in the resulting assembly. Prior to that, every single body was exported as an individual part file, but now this derives similar parts from, derive resulting parts from similar bodies or cut list. We'll take any identical components, export them only one time, and then build an assembly with the proper quantity of those. So that's the most important part there. So lots of great things with Weldments. Cut list interaction and on-screen interaction definitely top the list of those. One of my favorite things to show is this new chain component pattern. This tool is a mate. So performance-wise, any mate-based movements like gear mates versus intermittent collisions based on physical dynamics, really different when it comes to how their performance is with drag and drop on screen. So anything that's based on a mate is typically very good dynamic performance on screen. So let me show you a couple of use cases of this and then exactly how it functions. We're going to create something called an energy chain, and I want to show you the effect of what we're about to create. So we've had the ability to create things like this on screen for quite some time. Typically we take a component and we do a pattern along a path of a feature, but we added path patterns or component path patterns in SolidWorks 2014. So under linear pattern, you had a curve-driven component pattern, and that's how I would generate something that looks like this. However, this isn't just a look. I can grab on my sprocket, I can start moving my sprocket, and you can see that this chain is in fact physically moving. If I go ahead and grab on the master link of this one, and I think this just happens to be the original instance of this, but if I drag him around, you can see that it chases this odd path all the way around these three gears. So the performance is dynamic on screen. There's no delay whatsoever. What we're going to generate is this energy chain. And this energy chain is what we'd see on a lot of gantry systems, whether it's robots or 3D printers, but it has to do with cable harnesses and things that have to extend to devices up on the moving device without having those end up getting crimped or broken in the process. It's a management tool. So let me show you the process of creating this. Now the first thing I need to do with this is set it up a little bit. So what we have here is 4 parts in an assembly. This part that we have right here in the middle is free to move and rotate. There's no degrees of freedom taken up on this one. The part that we have up here on the top, if we take a look at the mates, is actually mated parallel to the bottom floor here, but there's no other mates currently on this component. So when it moves, it's going to keep its orientation, but it's free to move pretty much any other way. Part down here is completely fixed, and then we have a part that's not extruded yet, and it just has a sketch. That's this little energy chain sketch. For now, this part is floating, has a couple of mates left and right, so front plane, top plane, but for now, let's just go ahead and take that and fix it, because I do not want it to move just yet. So under your linear component pattern button, the flyout menu here has a new option called the chain component pattern. Now with the chain component pattern, we have 3 choices. We have distance linkage, and then we have connected linkage. So first of all, with simply distance. The chain path is going to be the piece that we select as our path. Now you got to be careful whenever you're selecting a sketch for something like a path, especially a sweep path. But when you see these buttons that say Selection Manager, that's cluing you into the fact that selecting might not be as straightforward as you believe. If I was just to pick on the screen right here, what I'm essentially going to pick is just the top line of that line arc line sketch. So you got to use the Selection Manager to make sure that you can pick open loops or closed loops or individual items that it would then dynamically group together. But by picking an open loop, I select that edge. I'm essentially group selecting the entire path. We'll say OK to that. Now the first component that we want on this chain is going to be this one, so simply fill it in. There is a link that you want to put on here. This is going to be where our first link happens to be, and it has to do with the geometry that we have, so our 2 pivots. If I grab any cylindrical or round edge that's going to represent that cylindrical face, that's going to be enough for me. And then path alignment, well, just for orientation's sake, I've got a plane over here. You can see that I've got that part canted a little bit, but if I use this plane for alignment, then it's going to go ahead and take that canted part and put the preview of it directly on the path. All right, so that's our starters. Let's go ahead and either fill the path, which will completely put a bunch of components on there, or let's just go ahead and put a decided number there. Now very nicely, we don't need that plane anymore, very nicely it's going to pattern this part along this path based on where that back hole happens to be. And like any other pattern, the nature of the beast is if I change the original, all the other components on that path are going to update. Not quite what we're looking for, but it's a step in the right direction. So let's edit that chain pattern. And we're going to switch this one from distance to distance linkage. Now linkage assumes that both parts of this link are going to be on the path. So instead of just one circle on the left-hand side, I've actually got 2. So we'll take our path alignment and we'll grab the second hole. Now that being said, what it will now do is it will put both of those holes completely on the path. And if we accept that and start moving things around, that's a lot more like what we're looking for. But once again, performance is very dynamic, very fluid. All right, let's edit this one more time. And this part is actually very simple with what we have here, and it's called the connected linkage. Because it has a first hole and a second hole, it's going to connect those holes sequentially along the way. Now an energy chain is built, so that's a one component. The back end of the one is going to feed onto the front end of the other and vice versa. So it's just going to be simply the same component in quantity. So as we give this a linkage, it'll take the first hole to the last hole, first hole to the last hole, first hole to the last hole, and so on. Now if this was a bike chain is going to be big link, small link, big link, small link. What you do is simply trigger chain group 2, pick the small link, and then set up first hole, last hole once again. Same way I set up this first component. So since we're doing one component does this, let's just drop that back a little bit. We'll go down to 18. This now gives us a really nice look here. So finishing this all up, let me just go ahead and finish mating these components together. So let's just grab a couple of round faces and make those concentric. Again, this one is fixed. And then let's just do a smart mate up here. So Alt key, pick and drag the edge of a circle, drop it in place. That parallel mate keeps that guy right where we want it. Now because this chain is actually applied now to a fixed path, because the red part, the chain sketch part, is actually fixed, we need to float this to get the full effect. Now if I grab the end of the energy chain and drag it forward and back, you'll see that because that chain sketch part can actually slide, that sketch will move position. Now that sketch isn't changing. There's no geometry changes. In fact, it's just a part moving back and forth. It's just not solid in this case. But that gives us the desired effect, and if this part was simply hidden, then you wouldn't even know it was there, and it would still give it the desired behavior. If we take a look back at this gantry, there is one caveat to this, and that is if the sketch does have to change. You see the one that we have in the lower right is the one that I just created for you. But up here, this one's a little bit different. As I start to move this hydraulic cylinder, or this actuator, the path isn't going to update until you hit rebuild. It is associative in the fact that it will rebuild properly, but because this sketch has dimensions that are changing, it is not a dynamic drag and drop situation. So we can always hope for future service packs if it's a critical game changer or mission critical, but for what it is, it works very, very well, and even in this case, it's going to work nicely. If you were animating this sidebar, if you're animating this in SolidWorks, every animation frame has a rebuild, so this would appear to move properly in the resulting animation. So there is a way to get the effect that you're looking for based on that type of a tool. Okay, sorry, I just need to clear my throat there. We are going to cover a little bit with sheet metal. There is not a ton of things with this, but the things that are there definitely have a lot of capabilities. So first thing I want to get into is an older limitation, which is now completely addressed, and that had to do with any lofted sheet metal component. We've had the capabilities to make these free-form shapes based on two sketches for quite some time. Now this is a classic example of rectangular to circular, a duct narrowing or a transition. We've never had the ability, however, to use sketches that were non-parallel, which this example obviously is showing us. If I go back to the raw version of this, you can see I have two sketches on planes that are obviously not parallel to each other. And when you select on your sheet metal tools to do a lofted bend, we're using some prep methods here where we leave a gap because, of course, you need the sheet metal part to be able to fold and unfold. But all we're doing is selecting these non-planar or parallel sketches, and as I select each of those, it's going to go ahead and give us the nice preview that we're looking for. Same thing I showed you on the Weldments. Anywhere that you have these magenta dots allows you to change from the overall defining characteristics of how many facets or the chord tolerance or length, and actually individually select those and modify them one at a time. So if I wanted to have many more facets in this corner than in the others, I could change that one up independent of the rest. It then turns blue to indicate it's no longer driven by the document's defaults. As I say OK to this, you'll see the nice preview. It turns into a beautiful solid part. And then the flat pattern of that gives us what we need, which is the number of hits in the corner in order to go ahead and make this on a press brake or on a CNC brake. But non-planar profiles, or non-parallel, excuse me. Very nice. So let's switch back over to our completed component. A couple of things to note on this one. First of all, when you flatten a part like this, last year, 2014, we added a gusset feature to the SolidWorks sheet metal components. When you flatten this, because a gusset by nature interferes with the bend, and on purpose in real life because that's going to give it strength, but as we flatten it, we need to remove it. So it's automatically put in the faces to exclude category of your flat pattern feature. However, when the flat pattern shows, we don't even know where it was. So under Tools and Options, there is a document property, so it lives with the file with the title block, or excuse me, with the document template if it's a sheet metal template for you. But it's down here to sheet metal, and it simply says show sheet metal gusset profiles when flattened, and then show their centers when flattened. And as soon as I do this, what you're going to see is a sketch representing those gusset locations appear on my 3D flattened part. Now, of course, when I uncheck flatten, it's going to remove that sketch and then show the 3D feature it is. But when it's in the flat pattern, that's got to be a keep out area. You can't interfere with where that gusset's going to go so that we don't accidentally punch a hole through it or put anything else directly adjacent to it. Every sheet metal feature has also had a preview, except for the sketched bend. So the sketch bend now has that. Let me just run through it and show it to you. As you sketch a bend, what you're essentially doing is taking either a pre-drawn sketch or drawing a new sketch, as I am in my case, and we're determining a bend that takes place around that edge. So as we go ahead and say OK to this line tool, it's going to complete the sketched bend by asking us for the fixed face, which will say this side's going to stay fixed. As that happens, you'll see the preview pop up, which it did not before. We'll go ahead and modify where the radius goes, the direction, and even the angle. Just make that 65. All right, and that should be parallel to the rest of those faces based on the angle of attack of that other face. But a preview is going to let you know this before we say OK, which was a little frustrating before compared to the rest of the interface. Last thing I want to show you on this is the creation of a mirrored part from a sheet metal part. Now, sheet metal parts I consider somewhat unique to other geometry because they're really more of a living, breathing thing. They start as flat material, and then they are bent up in an order and a process to create these 3D bodies, which kind of is more than just a milled part that you have a stock body sitting in your hand. So what happens with these when we try to use them in other places, and more particularly a mirrored, symmetric type of an assembly, is that we lose some of the behavior of that sheet metal resulting part. So SolidWorks 2015 has addressed this. What we do is we simply go ahead and take the plane that we want to use to mirror this component. We're just going to go ahead and use the right plane. And then we're just going to simply go on to Insert and Mirror Part. Now the choices we get over here are things like sheet metal information, which if I go ahead and actually select each of these, that's going to transfer the sheet metal information of the part over to the new mirrored part. Now these sheet metal details include a lot of things. It's actually the flat geometry, what faces we've deemed as fixed, the grain direction, so the way that this is going to sit on blank material, the faces to exclude, which will be the things from the gussets, as well as things like the bend lines and their parameters, any sketch transforms like the gussets in the flat pattern, and then the forming tool information. So basically the resulting mirrored part, though in reality it looks just like the original, simply the opposite, it actually has all of the functional behavior of an original sheet metal part. So over here is my mirrored result. If we look at the sheet metal features, we see that we have a part, and then underneath that it's actually going to list out all of the individual bends. So we have each of those and the ability to go ahead and take a look at those. But what we also get down here is the ability to see all the flat pattern features. And each of these bends also is going to have some associative information. As a result, if I click Flatten on this part, we're going to see a beautiful flat pattern that's exactly the opposite of the one that I showed you prior to this. And again, it has all the individual uniqueness so that we can go ahead and do things like individually suppress and unsuppressed bends. So anytime we're looking at this part here, there's a derived bend. We don't want derived bends for this particular one. We actually just want regular old bends. But that's going to give us some capabilities to take any one of these other bends here and just simply go ahead and suppress it. This one's got some interference on those. So essentially, the capabilities are there, and it's going to give you probably the most important part of this. Let's take that one back just so this doesn't change. But let me make a drawing from this, this resulting mirrored part. So the drawing from the resulting mirrored part auto-populates, but only if the sheet metal characteristics are there. So if I take a C-size piece of paper and we simply go ahead and make a drawing of this mirrored sheet metal part, so our part 2, once my view palette pops out, I'll grab my flat pattern, but you'll be able to see right away that as the mirrored part shows, it has all of that intelligence of bend angle, direction, radius, and the unique individual criteria for each of those bends to be created. So much, much more usable when it comes to saving yourself a lot of time by creating a mirrored part, but not losing the capabilities or the behavior of what a sheet metal part represents. All right, we got 2 more little sections here, and then I'm going to go ahead and check what questions have come in, and we will close out. So I'll get you right about 1 o'clock. So for consumer product design, there's some new capabilities that have to do with surfaces, both improvements to sketching splines on those surfaces, as well as something that we have called a flat surface. Now, flat surface I'll describe as I do it, but it has to do a lot with a basic interrogation of what a flat version of this 3D body would be. So let's go ahead and jump into those. I want to bring up my surface model for starters, and this surface model is what we call a shoe last. Anybody that's in the shoe industry recognizes these. They're for every size, and in many cases every half size of a shoe. And they're not symmetrical, as in they're not just a common upscale, downscale from size 3 to size 13.5. They're very unique in each of their incremental sizes. Within this part, which is an imported surface, we have a sketch. Now, sidebar here, first thing I want to show you on this sketch is that this has a spline in it. And the spline was generated with the original spline functionality that we've always had. The trouble I have with splines, especially when you have these interim points, is that those points get in the way of it being a smooth spline. They control the weighting, they control the angle of attack, they control a lot of crazy things when it comes to the way this spline geometry is actually generated. And it can make for a spline that isn't necessarily a nice, smooth transition from one end to the other. Well, now what you can do is right-click on any spline and actually convert it over to a style spline, which is now my spline of choice. What that does is it creates a spline based on prismatic inputs and a particular amount of geometry. And as I do this, it now gives you the ability to change the contouring of the spline by simply changing the weighting due to some prismatic construction geometry around it. But in any event, this spline is only 2 points now, so it stays completely smooth and never has those very abrupt transitions from convex to concave as a result of the way we make the input. All right, a little sidebar there. Well, we're going to take this sketch and do something we've never been able to do before, and that is the ability to go to my Surfaces tool and actually do a trim. Or we can always go ahead and go to our Features tool and do something called a split. Now the split would actually allow me to take this sketch and use it, projecting it onto that surface, to cut this surface into many individual pieces. So now individual bodies within this single part file. We're going to take all those and keep them. Visually, it doesn't look like we changed anything, but what we did do is we made 4 unique bodies. What that gives us the ability to do is select a body and actually isolate it from the rest of this design. Now this is a surface body, and what I'm going to do is go to my sketch tools, and we're going to sketch a spline on a surface. This feature also has been around for quite some time. So with this tool, we're going to just go ahead and select it and simply draw on the surface. And what's odd about this, and I'm saying odd in a very good way, is that it appears from the user that we're just kind of adding coincident points. So I'm just clicking once, clicking a second time, and then I'm going to infer to this edge back here and just double-click to finish it. So what this looks like, again, is just coincident points on a surface. But if I roll this around, the reality is that it's as if I stood above this surface and dropped a piece of spaghetti down on it. You can see that every point along that spline is completely coincident with that 3D surface. It allows us to manipulate this geometry by dragging it around. You can even see a delta change on that point as it wraps around the front of the surface. But it allows us to go ahead and make relationships and have very nice, clean geometry around this. I'm going to use that 3D sketch now, and in this case, we are going to do a trim. So on my Surfaces tool, I want to trim, and we can choose the piece that we want to keep, which is just going to be this nose of this boot. And that gives us this very, very organic shape and more of a bow tie type of a look. Well, now we can take this surface and do an operation called Flatten Surface. So with Flatten Surface, I'm going to window select here just to get everything, pick the ones I missed. But then we need a little vertex to determine where we're going to flatten from. And as we do this, we get a preview of it automatically. Now I need to caution everybody on this. This tool doesn't have a lot of inputs. We have high and low accuracy, and that's about it. There are third-party applications like ExactFlat, which is a product we represent, that will take into account the type of material that we're flattening. Because obviously if I was flattening fabric, which is a weave, weaves map to contours very easily, but leather does not. It's still flexible, but it doesn't like to bunch and stretch and thin and move with the shapes. So the material has a lot to do with it. Metals have stretch and elasticity factors. They're going to thin, they're going to bunch, they're going to oil can, and they're going to tear. And those are the types of things that ExactFlat would actually symbolize. Here we're going to get a nice look at this. We're going to show what is basically a good estimate representation of this. And it does generate a physical surface, so an additional surface to the originals. This surface can be interrogated by right-clicking on it and showing a deformation plot. But again, this deformation plot isn't based on a real sophisticated algorithm taking into account all of the factors. So it looks good. It's a great representation at this point, but it's only going to get better with user input on how we want to make this thing a much more robust type of analysis tool. And I'm not sure it's going to go much further than it is right now because, once again, we have solution partners out there that have great products that already do this. So unless the solution partner is going to embed their product into SolidWorks, which has happened frequently in the past, take this one with a nice representation, but not necessarily as a hardcore analysis type of a feature. Last thing that I want to show is going to be a fillet and a section plane, and it has to do with this new tool called Asymmetric Fillits. Now, asymmetric fillets, really the name speaks for itself, but I want to cover a little bit of the history of the fillet. Right here on the part, we have a round fillet. And since the dawn of time, every fillet that we've done in SolidWorks has been a radius, so it's been a tangent transition from one face to another. And in SolidWorks 2014, actually 2013 we started adding conics, but in 2014 we changed the profile capabilities to actually be able to make this from a circular profile to something called either a conic row or a conic radius. Now if we use conic row, what that would allow us to do is manipulate the geometry of this profile. And by changing the row value from 0 to 1, which is a ratio, by making it larger, we make what is really more of a parabolic fillet that is tangent to the start and end faces, but is a little bit sharper out at the end. The bigger that number gets, the sharper it is. If we switch that row value to something under 4.4142, it actually goes to more of a chamfered face, but there's still a tangency at the top and the bottom. So it's a completely different way to associate this. Same is true with the conic radius, it's just different numbers and input. Well, now what we've done is actually changed it up to allow from not just a symmetric fillet method, but to an asymmetric fillet. And what that simply means is different dimensions in different directions. So if here we say 5 in one direction and 10 in the other, what I now have is a trail off, or what we call a setback here on this fillet. We can switch directions, so the 5 is vertical and the 10 is the long leg. But in any event, that's now going to create a profile which is no longer based on a simple radius. This is now based on an elliptical shape. So once this finishes generating, you'll see how much more relaxed the surfacing transition, the fillet that we have between the top face and the outer body of this casting happens to be. This type of feature is used extensively in things like thermal forming, especially when gas tanks are involved, because gas tanks have an issue where you need to make sure that the integrity of the walls is clear everywhere for pressure concerns. All right, I've got a 3D point in the middle of this, and this is going to be the last thing we show. This 3D point here, I'm going to place a plane at that point. Now, plane at a point is nothing new, but orientation-wise, we would need some sort of secondary or tertiary input, parallel to another plane, through another edge, a lot of other things. Well, now we have a new input here, which is simply called create a plane parallel to our screen. So through that point, and now parallel to my monitor, when I click this button, it's now going to make a plane that's basically the white space of my graphics area. So if we roll that around, you'll see that it put it exactly where we thought that was going to be. Now, by using that plane, there's a lot of reasons we do this, but a lot of people like to interrogate their parts from just the way they're looking at it. And if I go ahead and take this plane and use that as the interrogation method, I can basically take section views like a CT scan here in the orientation that I happen to be looking. Now, this is also a very fluid type of thing as well. If I take that plane and use it as is, that's great. But if I take that plane and actually say edit, we can roll this to any orientation we want. We can then say update plane, and it will take a new flat plane based on my orientation. That way, when I go ahead and update my section view, same thing. We're just looking at it from the plane direction that we happen to be sitting. So with that, again, I want to thank you for your time today. Let me go ahead and pull over my questions box here and just see what kind of questions people have been asking today. And then we'll take a look here. Okay, so one of the questions is the mirrored sheet metal part a reference part or other derived parts? So example, the right-hand part is both sides update. Whenever you mirror a component, by definition, yes, it is associative to the original. So what will happen is at the point in the feature tree, actually the entire feature tree if the part does update and you add geometry, but the exported or mirrored version is associative to the original part. So if the original sheet metal component does change, then the mirrored part will change, and then any features that you've added to the tree of the mirrored component will then update after it in history. So yes, they are always associative. You can break it if you want to, but anytime you do a derived component, whether it's a mirrored part, even the save as assembly in the Weldments I was showing previous, that would also make the assembly that is the result of a multi-body part associative back to the multi-body part. So they all keep a nice link there. All right, so with that, I think everything has been covered with our session. And again, I want to just really thank you a lot for spending your lunch with us. I know you have a valuable time, and on a Friday you're probably getting ready for the weekend and got to get some things taken care of. So again, we appreciate your time. It's not lost on us how important this time is to you. So we hope this was a benefit of you. For any of you that are still holding on that would like to participate quickly here in one more poll, just want to see what features you maybe thought were not necessarily the most important, but maybe the ones that you thought were most interesting with this particular release of the software. Yeah, so I'm kind of getting some overwhelming things in the areas that I thought. BIM and MBD aren't getting much headway, but MBD is a brand new thing, so I'm sure that's kind of the first time many of you have seen that. All right, so it looks good on the poll. Let me just go ahead and share that with everybody, just to throw that up on the screen a little bit. So I figured Weldments would have been the most used, therefore the most important to most of you out there. And then the chain pattern is going to be interesting for anybody that's been trying to get this done, but really has never had a great method to do this. So once again, thank you very, very much for spending the time with us. Have a great afternoon, great weekend, and if you have any questions, please get a hold of us through either your sales rep or through our Decide technical support. Have a great afternoon.